Please start when you're ready. Pavana?
Yeah. Hello, everybody. Today, I'll be presenting a paper titled A Flexible Framework for Communication Efficient Machine Learning. And this paper was recently accepted at AAAI. Here's a brief agenda of today's talk. First, I'll introduce the motivation for the work. Then I'll talk about compression, the different methods, and some justification in the theoretical way. And I'll speak about this paper and the theoretical results that they present, followed by some numerical experiments and discussion. Then finally, I will conclude the paper. On the distributed machine learning settings, as we know, if we have different users having their own data set, these can be processors of, for example, some IoT devices or some other mobile devices or some other laptops in a system, in a room, etc. Those connected to a remote machine, which can act as a server, for example, a laptop. Assuming this kind of setting, let's say that each of the devices perform their own local training on the local data set by solving their local loss function or the local objective function. Let's say that we get the local model update, a difference with the global model update. These will be sent to the server or the laptop or any other central entity where it is aggregated, and then the global model update is computed, which is sent across to the participant devices, and this process continues until convergence. While this is a very important method and widely used, we know that the state-of-the-art problems that we have, which use the distributed machine learning, have millions of parameters. So they have a really large dimension. And let's say the dimension is indicated by D, then for a floating point, double precision numbers, let's say for 64-bit, you can see that the number of bits that is communicated per iteration per node can go up to 64 times D. So we see that this creates a huge communication bottleneck. So while there has been a long debate about the balance between the computation and communication, I think the earlier neural networks had smaller capacity where the computation would be very feeble. And considering larger neural networks and various advances that have happened in the deep learning, we see that the computation has quickened and the bottleneck has now again kind of shifted from computation to communication. And if you were to consider a neural network training, we see that if you measure the whole runtime, which includes both computation and communication, the entire process, we see that the communication can dominate up to 80% of the whole runtime. So given this kind of a...
Pavana,
yeah.
The communication here, are we talking about some narrow definition of wireless communication, or we're talking about more general, communication definition, like, in computing, you need to retrieve data from the memory through the bus or something. Some people call this one as communication as well. So what kind of communication definition we have here?
This communication that they're considering consists of the whole process of setting up your communication parameters and then transmitting the bits, receiving it, all of it combined together.
I'm still confused. So is narrow definition of wireless communication?
Yes, it's a little bit more narrow because in the beginning they don't mention that, but later on parts of the paper they talk about communication that includes the overhead of the whole communication part, where you're trying to set up the system, trying to retrieve the bits, store it, send it, etc. So they're considering all of that together.
Yeah, I have a follow-up question. Where is the 80% that the number comes from? At what kind of data rate they assume?
They are considering two different scenarios. One is the normal Ethernet, and they mention they don't say the data rate, but they say the number of bytes that they're transferring. I think I have it in like the later on slides.
Okay, but when you give a number, in particular, originally we're definitely communication group, communication networking group, right? So I definitely have that doubt.
Okay, yeah, I understand. Yeah, I should have mentioned it here. Okay.
It's not your fault. I just say, okay, in their paper, if there's a number there, it should be have some strong reference, solid evidence to show, okay, that number is true. It's not like you want to, magnify the value of your paper, then you randomly pick up a number without any kind of justification. Do they have any kind of reference for this one? You check the reference or not?
Yeah, actually, it's right in the paper. I can maybe share that. Yeah.
Do they have a reference for that?
No, it's their own measurement. They say they don't refer it to any. They don't have a reference, but they measured themselves, I guess. So they say that for a single precision, over like a 4G communication, they require like 4 megabytes of communication cost with a big model like 10 million parameters.
So where is the 80% is come from?
They don't have the 80% exactly written in the paper, but they have it in their explanation.
Well, whatever, at least, in several papers, we argue something related to the communication and computing, right? So even for your own paper, I don't know,
Right.
but yeah, I just want to say, okay, there's strong evidence to show everybody, okay, communication is the same. Yeah, finally, that's the end of the story, convince everybody, it's not like, okay, someone say communication is big deal, but someone say, okay, with this fast transmission rate is not a big deal, right? So I just want to make sure under what conditions, that argument or that statement is true. Right? Okay. Well, anyway, yeah. If they don't use the number, don't do any kind of deduction. You use that number. It's okay. Anyway, yeah. Move on, please.
Okay. So there are several strategies that we are aware of from the existing literature to reduce this kind of communication bottleneck would be to use asynchronous computation, where the server does not wait for each of the model update to arrive, but they have their own strategy to have this kind of asynchronous computation and communication happening. Or the more popular algorithms like federated averaging does a client sampling, where not all the participating devices take part in each round of communication or training. Rather, only a subset of the available clients are chosen per round for doing the training. Or you could set a communication period. This is something very close to the asynchronous communications, where you can set a time or a communication period where you will update the global parameters at that time, irrespective of how much of the local updates arrived or not. And the other most popular way of reducing this communication bottleneck is the compression, whether the weight compression or the gradient compression, but the model compression in general is a more popular way to achieve this. So talking about some of the popular compression methods that we have for reducing communications would be like using the existing distributed framework where the model updates are quantized or sparsified. They're basically compressed before sending them across to the server, where the server now would perform the aggregation of the compressed updates and continue to compute the global model, and this entire training can continue in this way. So here the Q is your compression, which can be, for example, sparsification, where you usually send some kind of top K or the most important gradient elements, or maybe you can use something like quantization, which basically tries to reduce the precision of the elements, or it can be any other compressor which can satisfy this kind of property. So the other set of compression that we can do for communication bottleneck reduction would be to directly target the gradients instead of doing the weights. So for that, you can compress the gradients and send the gradient updates to the server, where the server would aggregate the gradients and then compute the global model according to this. And this whole process can continue until convergence. So these methods are mainly used because we kind of know that they work well in practice. So given some existing methods, like let's say that this black line means no compression was performed, and the other subsequent lines would correspond to having the sparsification or the sparsification along with quantization or just the quantization, etc. We would see that for comparing a non-compressed version versus any compressed version, the minimum difference in communications would be up to, like, you would have more than 1,000 times of communication saving if you were to compare with the full precision algorithms. And this particular experiment was from their experiment setting, where they have the distributed data with server and one single node. They're located far away from each other. And this kind of experiment was performed to obtain this sort of a data. And what we have seen so far is, while we know, while doing empirically, we know that these kind of compression methods work well. Exact theoretical justification to say how exactly this compression is related to the communication efficiency is kind of, the link is missing. Following this very old work, I think most of the papers try to do a justification based on this, where we generally give an upper bound based on which you can say how much of compression is achieved and what's the convergence that we achieve by this. And we conclude from that saying that this is communication efficient, but we don't have a direct parameter to do that. So for example, the communication complexity for a strongly convex function is defined here in such a way that you would need at least d times, d being your dimension, times of log 1 over epsilon, epsilon being the epsilon accuracy that you would want to achieve. These number of bits have to be communicated to find an epsilon solution. So we see that there's a linear connection between the communication and the dimension. So the communication complexity grows at least linearly with d. And in the worst case scenario being, let's say, we're trying to do a sparsification and we try to do a top k, but let's say that the magnitude of most of the elements or most of your vector content are high enough. Like, you want to pick some highest magnitude ones, but let's say they're all, in the worst case scenario, let's say that they all have very similar or very equal kind of magnitude. So it's hard to choose the top k. The top k will have almost all of your gradient elements in your matrix. So in such kind of a worst case scenario, you'll see that even if you perform a compression, then you cannot see a major improvement in the efficiency. So this is what the worst case is, what they define in this way, and they try to address they use this term several times in the paper. So I mentioned it here. So this is one observation that this paper makes, that there is a lack of this exact theoretical justification for the communication efficiency through compression. So some of the challenges we see because of this is that most of the times when we perform any compression, we try to do the tuning of the compression parameter, whether we want a sparsification level or a quantization level or a pruning level or any kind of the sparsity, the compression levels need to be tuned carefully to see how much of communication benefit you can avail. But typically we kind of choose this value before we start the training. And most of the compression schemes we see are usually very generic. They're very agnostic of the different communication cost for different technologies you use. So you may not, so some cases you may use like a 5G communication link, maybe some other places you have a very much slower network. So our compression is usually does not really consider these kind of communication costs, no matter in what scenario you use. So given these factors, you cannot universally say that this is a universal good compressor that will work well on all the kind of problems, even if you have a worst case communication complexity. So it's hard to say that, one thing works for all. And also that since most of the papers give us a worst case bound, it's hard to explain the communication efficiency improvement using that kind of bound. And moreover, most papers rely on a very extensive hyperparameter optimization to achieve a very good communication efficiency. So these are the challenges that we see in the normal machine learning scenario. So based on these, there are certain contributions that this paper tries to make. First of all, they try to explain your communication efficiency by using some complexity bounds which are dependent on the data. So there are data or problem dependent bounds. And based using those bounds, they try to design an adaptive compression algorithm, which will maximize the communication efficiency automatically. And it also tries to adjust to the data which are present on. It tries to find a good balance between the communication and the optimality guarantees. So like we know, there's kind of a trade-off between how much of optimal solution you can get by doing the local training and how much you want to do the communication. So for example, if you want to increase the number of local iterations to increase the computation so that your the number of communication rounds or the number of times you want to communicate with the server with your model update reduces. So there is this kind of balance between communication and computation, or the suboptimal guarantee of your solutions that you would want to achieve. So this paper claims that they try to find a good balance between these two factors by basically focusing on more adaptive way of compression rather than a very deterministic way. And they try to strike this balance by adjusting the compression level online. For example, they try to optimize the number of bits that is transmitted per iteration. And using such factors, they try to find this good balance, and they try to contribute in a different way compared to the existing algorithms. So the initial setting, let's take example of the sparsified gradient descent, where you have the normal machine learning training, but you're using some sparsification. Let's say that your local model update per round would look like this, where the gradient is compressed, and the local model update is computed based on that. And Qt over here is your, let's say it is your sparsification with a sparsity budget T. So this sparsification can be defined as if your index, your element value has the largest absolute value, if it belongs to the set of IT of G, then you will set the gradient value as is, the GI, or you would set it to 0. So you're basically choosing some important parameters, gradients alone in your matrix, and that way you're sparsifying the values. So with this setting, like we've seen existing works, the sparsification actually helps us in communication efficiency. But why does it actually do? So this paper tries to give a different insight of that. They try to run an experiment with the previous settings of having one worker and one server, both located about 500 kilometers away. They're trying to run it on a data set of RCV1 first, and they're using a synthetic data set. And then they're also considering the worst case scenario of the one that I mentioned, of all your top K being important. So where there is not much of a communication efficiency that you see. So they consider these three cases, and they try to show this plot, and we can see that T being your sparsity budget, we see that for T over D, the worst case scenario shows no kind of improvement at all. And your alpha T is a new metric that they try to define. They call it as the proportional gradient energy, which can be defined as norm of your gradient over your normal gradient. So they use this metric, and they try to see how this kind of thing behaves. When in the worst case scenario, when using a synthetic data set in sparsification and using the normal training with the sparsification. Here we see that in the blue, you see the communications required is much lesser. So they equate this to alpha T. They say that the worst case scenario, the green line, this gradient energy, which can be defined as this, they say that this becomes equal to T by D. So which means that assuming that this kind of gradient energy is distributed evenly amongst all components. So they say that in this case, the alpha T will be equal to T by D. That's why you see this kind of a line. And for real data, for sparse data, they say that your gradient energy is actually concentrated only on a few components. So if you do a top K over here, you are choosing the highest magnitude elements. So that is where your most of your gradient energy or most of your information is present. So they say that this is the scenario when it comes to real data. So in this case, the alpha t value will be equal to greater than or equal to t by d. So they further, in the following slides, they further define the importance of this alpha t. And here to just give a small picture of how this metric is important, we can see that using this metric, it is very easy to see why or how much of communication savings I can make by performing compression. And here the Q can be replaced by quantization or any other different compression methods, but by applying that here, theoretically, you can kind of see the influence your compression is going to have on your communications. So this is the main explanation that they give. This is the first contribution of their work. And while this is kind of empirical and they use this metric further to show a theoretical way in how this is justified. So given this kind of an update rule, and if you have a step size equal to 1 over L value, they show that the objective update is going to be of this way, where this alpha t plays a major role in defining your conversions. So we can see that this alpha t implies any kind of progress your sparsification method can make in each iteration. So most of the times we see that we have a sparsity budget we define in the beginning, and with each iteration we do a sparsification, and then we do the local training, or we do the local training and then the sparsification. So basically iteration by iteration we're achieving more sparsity. So using this metric directly here, you can kind of track and see how does the kind of progress you're trying to make in each iteration. And in case where you are not doing any compression and you're just doing a normal gradient descent, this value of alpha is going to be just 1. And for the worst case scenario of all top k being the same, for that it can be equal to t by d, like we saw in the plot. Or otherwise we can set alpha t, it's basically greater than or equal to t over d for all the basic general scenarios. So theoretically, this is how they are showing or proving a connection between the compression and the communication directly, and how you can see the progress. So based on this, they try to show the iteration complexity from their lemma. And their 3 scenarios would be the strongly convex, the convex by C, and NC means the non-convex setting. They show what is the upper bound for the non-compression. So these values of SC, AC, and ANC are defined over here. These were taken from some reference papers from some standard works, which have already proved the upper bound. And the third row talks about the worst case scenario of what they find out. The worst case scenario is nothing but the T by D like we saw last time. So now the values will have the same as non-compression versions times D over T. So between these two, we see that the number of communication bits probably will not have much change, but the iteration complexity is kind of worsened by having this kind of a worst case scenario, because you have your T sparsity budget and D is your dimension. So it's kind of worsened in this case. But if you consider the second row, which is the work they emphasize, they have the same A values, but on top of it, they have their new metric alpha, which is an additional parameter that is added over here. So what this does is, using this, we can see that there is a hypothetical speed up that is achieved by sparsification in this scenario. If they give this kind of an equation to measure the speed up that your algorithm can achieve. So let's say your speed up would be equal to d over t over 1 over the alpha value. So given that, we see that whatever value you measure for alpha, you can use that directly to see theoretically you can have a proper value of how much speed up you're trying to achieve by using this kind of a sparsity budget or using this kind of a compression method. So this is the speed up that you can directly measure. You can also see how much of compression you're trying to achieve in terms of communication bit. I mean, you can see how much communication bits you're using for each of the methods. So in case of no compression, you see that for a 32-bit precision of your gradients, it'll be equal to A times D. And for the worst case, also, it is going to be the same thing. But for data dependent scenario, you would see that this would actually be directly dependent on the sparsity budget over your alpha value that you set. So that way we can see that the number of bits that you're communicating per iteration is going to be reduced depending on what is your budget you're choosing and what is the communication parameter that you're choosing. So this is the main thing. So based on this, they try to explain the same graph again, saying that for many real data sets that they use, the value of this 1 over alpha is going to be very, very, very less than D over T. So it is not completely dependent on your dimension that you have of your data. So you have now come up with a new metric, which is dependent on the data, yet while it is explaining how well your communication is working, you can also see that there is a 1,000-fold of communication improvement in this scenario. So this is the main idea of the paper. Any questions so far? Okay, if not, I'll try to explain the theory in more detail. So for any compression method that you consider, whether sparsification or quantization, for example, let's say here we do the sparsification. The main idea is to have a more adaptive way of choosing your sparsity budget. So you will first try to find the sparsity budget T, make sure that it maximizes your gradient descent per iteration. So for that, you can use something called as efficiency, which is nothing but your alpha value over the communication cost. So you're trying to do an argmax of this. So this ratio of alpha over cost usually attains its minimum over t values of 1 up to D. So these both values can be measured online. That's the major advantage of it. And your alpha value can be easily adapted to whichever compression method you use, like we saw in the previous slides in the definition of alpha. And so this solves the main challenge that most of the compression methods are very not very flexible because you try to find the budget in the beginning before training. And the second challenge of the communication is overcome by using this cost. This cost is nothing but you adapt it to the technology or application that you use. So this cost is defined in this way. Let's say C of T is nothing but the cost. So what they consider is for every packet of the information that you send, you have the payload and you have the communication overhead. So they say that not a lot of people try to highlight this part, but they highlight this saying that your communication cost consists of both your information, that is the payload part, as well as your communication overhead part. Here, C1 is nothing but the cost of transmitting one single payload byte. Your P of T is your payload. And Pmax is nothing but the number of payload bits per packet. And C0 is the communication overhead that can be measured. And how do you check how many bits that you need for the payload is you can use this kind of a relation where first, if you're using a sparsification, your payload can be defined as your sparsity budget times the log of your dimension plus the precision value you're using. The full precision would be, single precision would be 32. If you're using a double precision, that this would be a 64-bit. So you can use this to define the payload for the sparsification. When in terms of quantization, you can use this kind of a relation. So basically, you compute your PT based on this, and you can obtain the number of payload bits per packet with the Pmax. And for C1, it would be the cost that you would need for transmitting a single payload byte. This depends on what kind of communication technology you're using. For example, if you're using, they give us example of if you're using just the Ethernet to transmit one single UDP packet. So then your C1 would be equal to 1 byte. So 1 byte, so it is just considered as one. And the C0, which is the communication overhead, would be 1 byte, that is the 8 bits of how much you're transmitting, times 54. So you can have this number of bytes as your communication overhead, and you can have the payload up to 1472 bytes. So your entire packet can be defined like this. So now you know that depending on what kind of communication technology you're using, you can flexibly define your communication cost. So this in turn, and the alpha, as we know, was dependent on the kind of data you use and the kind of compression you use. So that, and we are also now considering the communication technology that you're using. So in a combination of all these things, now you're trying to find your compression level or your sparsity budget. So this is a more intuitive, I mean, this is a more better way of finding what is the budget that you want to allocate for compression for your training. So we can do this kind of computation and then count the, and then compute the T. So what the algorithm goes like is, this is just a framework that can be put in any existing compression methods like sparsification, quantization, etc. So they don't have a separate algorithm, but they just have a couple of steps that you need to perform in your normal training. So given your communication iterations, the first thing you would do is you would try to adaptively tune the budget, the compression budget that you want. So like we saw, the computation of T considers all kind of parameters, the communication and the data. It considers all kind of parameters to compute the T case. So you can tune it accordingly. And they say that because T can be chosen in a more realistic way, you don't have to do a hyperparameter search to compute T, or you don't have to do extensive hyperparameter optimizations to do the training. They claim that. And once you have your sparsity budget or your compression budget defined with you, you can use that to do the compression and continue with your local training. So as we can see, the other difference we see here is, like most papers, they would define the compression levels or the budget in the beginning of the training at one time for all the iterations. This paper gives us a flexibility to choose the value of the sparsity budget at every iteration, given the data, the network conditions, and what is the data that you have. So it's basically online. Instead of doing everything offline, you're doing the whole tuning online. So this way you see that this will be a more better way and a more easy way to do the compression. So this method, they say, can be extended to other methods, like you can use both sparsification and quantization together. Maybe you can define a compression function in this way. Or maybe you can use a stochastic sparsification, where if you use a stochastic sparsification, you can maybe use a Bernoulli distribution to define your P and do a multi-node optimization, etc. So you can really extend this framework to different kind of compression methods. And for the communication cost, they say that there are many possibilities. They say that right now we were looking at the number of bits transmitted. They say this can be easily extended to the energy or the delay, the transmission time, etc. And they can say that right now we were talking about the communication cost, using what communication protocol you're using, what standard you're using. You can build based on that too. Or you can even try to use some empirical measurements, maybe have some historical data. Based on that, you can try to adapt your T according to that. So you have many possibilities in how adaptively you want to do your training. And in terms of defining the cost, there are two ways that they define. One is just the fine cost, if you want to use, would just be C0 plus C1 times of T, where C0 can be looked at your packet headers, and the C1 will be your cost per entry in your header. And for Ethernet, like I was showing in the previous slide, you can see that the C0 would be 54 bytes, and C1 can be 4 plus log 2, and or you can do the empirical measurements like this figure over here, and also try to get the historical data to do your tuning. Or you can find the whole packet cost, like maybe if you're using an Ethernet, then for the cost, you can use both the communication overhead part and the payload part, like we saw in the previous slide. Or you can use some other technology like low energy wireless, etc., to use any of these to basically tune your sparsity budget and do the training. So these are all the theoretical part of this paper. Next, I have some experiment settings. If you have any questions, you can feel free to ask. So for the experiment, they're doing some real
Pavana, what's the paper trying to say? I can say two things, okay? The first of all, compression is good, right? So they find some theoretical proof for that to show, okay, compression is good. Yeah, I can understand that. That's good. But the second thing is, okay, compression is good. I want to use adaptive compression, right? So I use alpha T or whatever. But for this adaptive compression, when I use that, I need to consider the communication cost, right? So I define a very general communication cost function. That's it, right? So according to the communication, I do corresponding compression. I adopt corresponding compression techniques, right? But the thing is, in general, right? For example, in several papers we have seen, like you mentioned, in the optimization approach, when they consider this, they not only consider, say, probably they didn't consider much about the communication. In some of our own paper, we consider some of communication part, but many people consider, okay, the compression impacts on the learning part, right? It seems this paper give a very simple metric. They didn't even care about the convergence or the convergence rate or something. You know a point here, right? They only consider, okay, a high level communication cost to adjust the compression approach correspondingly, right? But they didn't consider the learning performance here.
Okay, so Dr. Pan, differing from the other rigorous optimization that we usually do, the whole idea of this paper is to make it so generic that it can be used in any kind of situation. I think in most of even our own work, when we try to use the compression, we have some specific things that we say that maybe I have a GPU model, consider some values from there, and so it's
I got your point. It's like an early stage of routing protocol, right? So I just define a very simple metric. You follow this, like shortest distance, minimum hop, in terms of something like that, metric like this. Then you follow that, then you can achieve pretty good performance, but it's not necessary to be the optimal. Are they trying to do something like this? You know the routing, right? So in wireless ad hoc network, there are several protocols, right? Distro and ETX and some shortest distance, minimum hops, right? So we have different ways. Then later people find out, physical layer routing or something. But the thing is, for routing, our assumption is we have a very high uncertainty ahead of that. We cannot predict that, right? But for this learning, you develop something like the routing metric. You even don't consider the convergence part of the learning, not to mention the loss or accuracy. Yeah,
they do, Dr. Pan.
They do?
They do consider, yes. The lemma over here, I only mentioned for this the sparsification, but for each of the compression that they consider, they do talk about this whole convergence part. They have the learning convergence, so they show that the accuracy will be much better if you use this method.
Okay, so when you design alpha T, you also consider the convergence part.
We are considering the data and the gradient at that point. Like when we do the alpha T, we are more interested in the gradient in every round. Now the gradient would be dependent on the data and all the learning parameters that you choose. And they even define what is the step size that you need to use for any of the compression that you're using. For sparsification, they give this. For quantization, they show like different kind of step size. So they have a rigorous theoretical proof, which also includes the learning part.
Okay.
So it is quite analogous to what we try to achieve. So they do consider all the learning parameters along with this communication cost. So that was the whole intention that I thought I'll present this paper, because our group was very aligned with this kind of compression communication work. So I thought using this kind of flexible framework in our own papers, maybe we can try to achieve some better result, because we do the optimization part, and this paper is proposing some metric for the specific for the communication. So I thought maybe this can be very useful in our own work.
Well, what I'm trying to say is it's like they propose kind of a metric, right? Instead of so what I feel is it's always kind of yield a kind of a suboptimal solution. Like you mentioned, they didn't consider some specific problem setting, right? So they considered a very generalized problem setting. So if you follow their approach, most of time compare with the complicated optimization like you mentioned, we can have pretty good solution, but that's not the optimal one, right? If you use optimization or some other existing approach, probably you can have better, more close to optimal solution than this one. You know what I'm trying to say here?
Yeah.
This one is very generalized, right? Just like I mentioned, like the routing metric, right? So it's very generalized. It works. It works well. But as long as, say, if you know the source and destination, you know the graph, you know the whole graph. If you don't care about the complexity, you want to solve that overall problem, travel salesman problem, whatever, you can find the optimal path. And the optimal path is not necessary to be consistent path you find out to use any kind of routing metric. You know what I mean here? Yeah. Can. What I want to say is, okay, probably this project can give you a kind of good solution, but it's not. We cannot justify, okay, it's optimal or something. But on the other hand, yes, it can significantly reduce the complexity if the alpha T function is not that complex. Okay.
Yeah. So yeah, I understand your concern. I think if we have to compare it with our own works or like other maybe related works, so maybe we have like the energy, or we have probably the delay or something as the highlight, right? We formulate the problem on the basis of that, and we try to tune some hyperparameters. Maybe we use the batch size or something like that. So what this paper is doing is something very similar. They say that you can formulate the objective to use the energy, or you can use the delay or anything. And instead of using the other hyperparameters like maybe batch size or something, you don't have to depend on the hyperparameters at all. Instead, you can just use your existing sparsity budget or your compression level as a hyperparameter and just find the optimal T. So you find an
Yeah,
optimal T, and
yeah, I got your point. It's kind of online approach, right? So this is exactly, I want to, compare that with the routing metric, the routing things. For routing, yes, it's also the same. It's online, right? So you need to determine your next step, something like that. Yeah, I'm not saying it's not good. I'm just saying, I don't know, how can we further improve this paper, or say, how can we further work on something similar to this?
Okay, I think maybe we can try to make it like energy efficient, have that as a formulated problem.
No, that would be a kind of it can be a subset of their their problem, right? So yeah, we can definitely specify that, just like I mentioned, at the beginning for the ad hoc network routing, people propose a very generalized approach. Later, people specify that, right? To some security-based routing, physical layer-based routing, this routing, that routing, a lot of routing, right? They propose a different metric. Yeah, probably. Second thought, I think it's not necessary to be a bad paper. You just open another door for us to do the analysis, right? Instead of focus on the, very complex hyperparameter selection things, optimization things. We can develop some simple but useful metric. Yeah, okay.
Yeah.
Okay, now I'm more in favor of this paper. Okay.
Yeah, and I think like if you look at multiple nodes, or maybe like this kind of lemma 4, you can kind of see the contribution that it has for our convergence analysis the way we do. They have considered all the learning parameters very similar to that. And they're trying to use their own new metric, like in between, and try to do the same kind of verification that we try to do. So I think this approach is kind of convincing. They just introduced very simple thing, like you said, it is actually really simple, but it is really effective. They have like better accuracy, they have better communication, all of that. But yeah, the paper also has few limitations. Maybe I can get to that in the next slide.
Okay, yeah, please go ahead.
Okay. So we were talking about the experiment. So this paper, instead of doing the simulation, they're doing the real experiment. So they consider two settings. One is a single master, single worker, kind of a single node setting, and the other is a multi-node setting. And in the single node experiments, they're using the framework. Their framework is called CAT, basically the compressive adaptive tuning. So they're first verifying with the sparsification plus quantization, the dynamic compression method. They're using the URL dataset, which is really huge. They have like 2.4 million data points and about 3.2 million features. And they're using the distributed data. And they say that the data is present on the worker, which is located like 500 kilometers away from the server. And they use a ZMQ library, and they use a 1000 megabit internet connection between the server and the client. And with this, they show that their loss, the f of x training loss versus the communication time in milliseconds, you can see that the blue one is no compression. You can consider it as the normal gradient descent. And the red line dot is the very famous Alistar's paper of sparsification plus quantization. And the versus the green one, which is their own paper, where they're also using the sparsification plus the quantization. we can see that this CAT outperforms both the algorithms here. And in terms of the communication time, we can see that it is almost up to 2 orders of magnitude better than the very famous dynamic sparsification plus quantization paper. And
excuse me,
compared,
sorry to cut in. So for the Alice star, it's kind of fixed sparsification and quantization, or it's kind of also adaptive dynamic sparsification?
it is not adaptive, but it is dynamic.
So cat is adaptive one, right? So Alice star is a fixed one.
Yes, Alice star it would be the fixed one.
So did they compare with any kind of adaptive sparsification and quantization scheme?
No, not with any adaptive ones, but Alice stars is more dynamic. Like they choose different values based on the dynamic setting in your iterations. So I think that's why it is very close to that. They don't have a fixed level.
You said Alice star is a fixed sparsification and quantization.
No, it is dynamic.
It's dynamic. Okay.
Yeah, it is dynamic.
But they
follow, don't tune it like
they don't tune that.
It's like it's like the standard sparsification quantization that we have seen. It does not consider the communication like how this cat is considering.
Okay.
Yeah. So compared to the most popular and standard algorithm, we see that this cat performs better than that, and also it has several magnitude better compared to no compression at all. And the other settings they have is for the multi-node. For the multi-node, they verify 3 different kinds of compression. One is the deterministic sparsification, that is the stochastic sparsification, and the third method of sparsification plus quantization. So the CAT is verified on all these 3 compression methods. And they use a Reuters news dataset, the RCV1, which is also very huge. It has about 47,236 features and 600K plus data points. And the wireless communication scenario that they assume is the IEEE 802.15.4, the low energy wireless, which has a 512 byte packets of payload. That is the one that they're using. And the multi-node setup is they have 4 nodes, and the communication between them is through the MPI. And they split these data evenly amongst all the nodes. And the result of running that, the loss over the communication in 10 power 9 number of bits would look like this. So for a no compression, iteration by iteration, we see that there would be no difference in the communication bits. It would be the same. And for just the sparsification alone by this paper, we say that it is a little better than the no compression, but it is not as good as Alice star's sparsification plus quantization, because they're doing 2 different compression methods together. So the Alice stars would be better compared to just single kind of a compression. But compared to the sparsification plus quantization doing a similar compression, but using this algorithm, the CATS algorithm, we see that it really outperforms way better, and it is almost 6 times more communication efficient compared to Alice star's method itself for the same exact compression scheme. And also considering that all the algorithms try to reach epsilon value of 0.4, we see that the communication value is much better, and also the loss is decreasing much better. So the convergence is also good, and the algorithms achieves better accuracy compared to other methods. So these are the experiments that they do. They also do some smaller verifications, that is like with respect to the value of t, etc. I did not put those figures, but these were the more important ones. With these, they also state a couple of open problems that they have. They say that they're trying to work on some.
They only show the training loss, right? So do you show the testing accuracy, something like that?
Actually, I was trying to look for their appendix, but I couldn't find it on time. But I found it later. But they say the number of bits required to reach the accuracy value, but they did not show the test accuracy like the way we do.
Okay.
Yeah, they just showed the convergence part through the loss.
Well, it's pretty obvious they can outperform, Alistar because they consider its communication cost. But what I'm interested
Yeah,
in is if you consider that,
accuracy.
yeah, how about the accuracy compared to Alistar?
Yeah, that's what I was trying to find, but they didn't. But I was listening to a talk by one of the others in a different forum, and they were mentioning that they have better performance. So I was assuming they're
Okay.
talking about test accuracy, but they don't have that in the paper.
All right, then you don't need to apologize for the author. So I think, but they should show that, right? So if you want, even their performance a little bit worse than Alistar, I think it's acceptable. But if you don't show that, it's kind of weird thing. Okay.
Yeah. So it was difficult to put a finger and say the accuracy is better or not because I don't have proof to show that.
Yeah,
So
because for all this figure they show, that's obvious. Because they didn't consider, Alistar didn't consider the communication cost. You consider, you should be better than that game. But if you only show the convergence of training loss, then yeah, not that convincing though. But anyway, yeah.
okay. So with all these experiments, they state a couple of open problems that they have. That they did the verification mainly on the single node and the multi-node setting, but they say that on the federated optimization, they are yet to, excuse me, they want to do the complete implementation on the federated optimization. And they say even the popular error feedback that we use and all the equivalent to error feedback like Diana, etc., they say that they haven't verified the CAT on that, and they would they are in the process of extending their paper to run on all these kind of frameworks. However, they do give us a theoretical analysis of how the CAT would behave when you use a distributed architecture. They gave a couple of lemmas and what kind of communication complexity can be reached. And they also introduced like some constants, and they show that their method can be extended in a theoretical way also to distributed architectures. However, they say that the current scope for this would be that the compression level that you're choosing would be the same for all clients. They want to extend and make it make different compression level for different clients. They say that they're working on the theoretical proof for that. And they also show a lemma, they prove a lemma for the distributed stochastic falsification method too. And they give us a proper analysis of that. But however, they have a couple of open questions again. One is to say that how do you tune the local compression level without doing the synchronization? Because like at every iteration, you send the model updates and things, so you're kind of dependent on that. So they were trying to tune the local compression level without doing any kind of synchronization. And the other would be to how would you tune this kind of deterministic compression for the federated architectures because of the non-IID data that the clients would have. So these two are the other open questions that they have. So that's what this paper introduces. So compared to the existing work, they say that the worst case bound that most papers talk about, the upper bound, does not really explain the communication efficiency that is given by compression. You don't have a direct connection between the communication and compression in a theoretical way. And they also say that the existing work show compression, but they're not really adaptive to the relevant technology you're using or the communication costs that you have. So over these limitations, the main contributions of this paper is to first of all explain what is the improved efficiency of communication if you use compression. And they give us a new metric, which is more data and problem dependent. And they also design an adaptive compression method, which optimizes this overall communication efficiency automatically. And it adjusts to the data online and to any of the communication technology you give, and it leads to significant communication savings compared to the existing compression. And the open problem, like I was mentioning, they would want to extend the framework both theoretically and full-fledged experimentally for the distributed and federated optimization settings. So that's all I have today. Thank you so much for listening.
Any
Any
questions?
questions?